Okay. So just start?
Yeah.
Okay. Hello everyone. My name is Kang from University of Minnesota. And here I will give you 5-minute version of my, maybe more than an hour version of my talk. It will be about fracture media, and also it will be about inertia effect. So maybe not many of you thought about this problem, but it can be very important in natural systems. And in this talk, I will show you how the fracture media can really govern subsurface flow. And more specifically, I will talk about how fluid inertia can really fundamentally change transport processes. So just start from the bit of larger picture. We know that if we see the cross-section of the subsurface, we do start from unconsolidated porous media, but soon we will hit fractured bedrock where the flow is governed by discrete flow paths. So this is how natural rock, fractured rock look like. And as you can see here, most of the flow preferentially flows through fractures because fracture permeability is typically significantly higher than rock matrix permeability. So just to highlight again the fundamental difference between fracture media and porous media. If you see downbore video, here you are looking at a water really gushing out through a discrete bed parallel parting, and this is because of the local fracture permeability being really significantly higher than the rest of the rock matrix. And this is sandstone aquifer, and even in sandstone, this kind of bed parallel parting can significantly develop. And you even see this kind of sediment swirling motion, which is an indication of strong fluid inertia. So in this full version of presentation, you will learn about how inertia effect can fundamentally govern flow and transport phenomena, starting from solute transport in single fracture, where you will see this kind of small recirculating flow could trap particles and leading to a anomalous behavior. And then we will move on and think about how inertia effect can fundamentally change mixing and reactive transport. We will particularly focus on fracture intersections, which is known for biogeochemical reaction hotspots to porous media. And finally, we will talk about mineral precipitation, again in the context of fracture intersection. And I won't have time, but we also study how fluid inertia can affect mineral dissolution when the porosity is actively increasing. So as a key result, this will be my last slide. I just want to show the key message from this presentation, which is, again, the fundamental impact of fluid inertia on reactive transport, and this is for mineral precipitation. So this is lab experiment, and we are really visualizing how the mineral is precipitating when the two fluids with two different components lead to the mixing-induced precipitation. So I will play this video again. And the only difference between the two experiments are the flow rate. So the left side have 10 times slower flow rate than the right side video. And you can see that 10-time increase in flow rate can fundamentally change the mineral precipitation pattern. In the full version of my talk, I will go in detail and explain how the change in the fluid flow due to inertia can lead to this fundamental change in the precipitation pattern. So hope this was interesting, and if you want to learn more about it, please look up my full version of the lecture. Thank you.